This is the pencast for section 1.8, tangent line approximation. And the whole point of this section, which is really one of the most important sections in the course, is that if we have a differentiable function is what we call locally linear. In other words, we can use a line to approximate function values, at least near a point. And so that is our goal. We want to see how we can approximate a possibly very, very complicated function f of x using a line. And this approximation will be what we call local, so it may only be valid sort of near a certain point, and we'll discuss how we might actually use this approximation in class. But let's first talk about what this approximation is. So, if you do not remember how to write equations of lines, you should stop the video right now, go to Khan Academy and find a video about how to write equations of lines, and then come back to me. Okay, good. So, what we're going to talk about now is the tangent line. We've been talking about it a lot. The tangent line to a function at a point is the line that touches the graph of the function just at one point. So we know some things about the tangent line. Let's suppose that we have a differentiable function at a. Why do we need differentiability? We need differentiability because that tells me I have a unique tangent line at a given point. Now, if I have a differentiable function, then the derivative at a point a tells me, that's right, the slope of the tangent line. I know one other thing about the slope of the tangent line at a. Namely, by definition, what does it mean to be a tangent line? It means it goes through the graph of the function at one point. Which point is it? It is the point a, f of a. So this is what I know about a tangent line at the point x equals a to the graph f of x. It has a slope, f prime of a, and it has the point a comma f of a being on it. So here's a picture. I have a graph f, I have a point a, I have the corresponding point a, f of a. I draw the line, the tangent line through that point, and that has the slope f prime of a. Now, as you know, one way that I can write the equation of a line is using point-slope form. So if I do that, the equation of my tangent line is just y minus f of a equals f prime of a times x minus a. And if you're thinking about the formula for point-slope form, that f of a is y1, f prime of a is your slope, and a is x1. So we have y minus 1, y1 equals m times x minus x1. So we just put our information into point-slope form, and there we go. We have the equation of a tangent line to the graph of f at a. And if I want to make this look a little bit more like the equation of a line, y equals something, if you like it that way, then we can solve for y, and we get y equals f prime of a times x minus a plus f of a, and this is the equation of the tangent line to f at a. Okay? So we've written the equation of a line. Great. Now let's see how we're going to use that equation. And this is something called the local linearization. So we will say that the local linearization, L of x, is f prime of a times x minus a plus f of a. This should look very familiar. This should look just like the equation of the tangent line, except on the left-hand side, I wrote L of x instead of y. That's on purpose. We are now thinking about the equation of the tangent line as being a way that we can use our line to approximate function values. So notice here that a is fixed. So f prime of a and f of a, those are fixed quantities. What I can do now is I can plug in different x values other than a, and I'm using the equation of the line to get an approximate value of f of x. So again, here's the picture. We have f of x, we have a, and I have L of x. So that's the tangent line that we computed using point-slope form. Now instead of calling it y, I'm calling it L of x. Now here's what I can do. Let's take a point B that is nearby A but not equal to A. Then the point B comma L of B I can calculate very easily using the above formula. Notice that that's a pretty good approximation. It's pretty close, the y value is pretty close to the point B, f of B. So we're using this line, values on this line, L of x, to approximate function values. Because near A, a differentiable function is kind of like a line. It's locally linear. So that's what we're doing here. That is the whole business of local linearization. And in math symbols, for x near A, L of x is approximately equal to f of x. And we sometimes write this as f of x is approximately equal to f prime of A times x minus A plus f of A. Now, those two things are not exactly equal. That's why we use those curly kind of sort of equal, almost equal, equivalence signs. So there can be an error. So let's talk about whether L of x is too big, too small, or just right. And can we know ahead of time if our local linearization is going to give us a prediction that's too big, too small, or just right. So let's say I have a function f of x. This happens to be an increasing function, but it's also concave down. Notice that when I have a concave down function, the tangent line is going to lie completely above the graph of the function. So that means that my prediction from L of x is going to be too big. So L of x gives me too big of an approximation if and only if f is concave down. Now here's the graph of a concave up function. And again, notice that for a concave up function, L of x lies completely below the graph of f of x. So if L is too small, if and only if f is concave up. And what if I have a graph of f of x that looks like this, a straight line? Well, then we know that the tangent line is exactly the line itself, so L of x is just right if and only if f of x is a line. And different errors on either side of A can occur at points where the concavity changes, but I'll leave that to talk about in class.